Okay, so let us start the problem. This problem says air has certain characteristics, nothing but gamma equal to 1.4 and R value, that characteristics gas constant 287.43 joule kg per Kelvin. Enters a straight axisymmetric duct at 300 Kelvin, 3.45 bar and 150 meter per second, and leaves it at 277 Kelvin, 2.058 bar and 260 meter per second. The area of the cross section at the entry is 500 centimeters square. So by assuming the adiabatic flow condition, what we have to do, we have to find out stagnation temperature, maximum velocity, mass flow rate, and area of the cross section at the exit. Okay, so this problem is similar like our previous problem. In the previous problem, what happened? Mach number, entry and exit Mach number were given. So in this problem, the entry and the exit Mach number, okay, is not given. But what happened? They are given another parameter, that is temperature and velocity. Okay. So with that, we can find out the entry and Mach number. So that is only the difference here. You have to see. See, the thing is, by using the entry temperature, that means static temperature and velocity, flow velocity, and how we are solving. Okay, because the entry of the axisymmetric duct is given, the velocity, what is the velocity at the entry? That is given 150 meter per second, and the exit velocity is given 260 meter per second. So we need to find out then by assuming the adiabatic flow condition, and also the assuming that by considering the cross section at the entry. So we have to find out stagnation temperature. So in order to find out the stagnation temperature, first of all we have to understand certain things. So adiabatic flow, since it is adiabatic flow, so what you have to see, there won't be any heat transfer. Okay, so if this is the case, then what happened? There won't be any losses as well. So that means since what the heat transfer is zero, so the losses will be nullified. So in that case, you have to find out stagnation temperature. So stagnation temperature, you see here, we know the formula, the basic formula in the gas dynamics, or in the isentropic flow. This is the basic formula. This formula, you know how we have derived. Okay, so this is a basic formula. That means T naught by T equal to 1 plus gamma minus 1 divided by 2 into m1 square. So when you are subscripting the T equal to T1, then m1 also should be taken as m1. Okay, so that is the idea. So that's why T naught by T1, then here m1 comes. So now what you supposed to do, you have to just substitute the value. Okay, because first we need to find out stagnation temperature. So for finding the stagnation temperature, we need to have a Mach number. Okay, so m1 is required. That is nothing but entry Mach number is required. So in order to find out the entry Mach number, then we are using this formula. That is nothing but m1 equal to v1 by a1. So v1 is nothing but flow velocity. This is a1 is nothing but speed of sound. So then v1 is given at the entry condition. What is the velocity? That is given at nothing but 150 meter per second. And a1, so that is nothing but square root of gamma RT. So those values also is given. So gamma is nothing but 1.4. Then the characteristics gas constant nothing but 287.43. So if you want, you can take instead of 287, you can take 287.43. So that also I think you can just make it. Okay. So here you can just what to say? Yeah, this at this point you can include this. Okay, so that means 287.43. Okay, so this is nothing but this. So then into temperature. Temperature is nothing but static temperature at the inlet. So that is given nothing but 300. So if it is given in degrees Celsius, you need to convert. Since the temperature in the problem itself given as the in degree Kelvin, so we are taking it as 300. Okay, so that is one thing. Then yeah, so after substituting all, we are just we got the value that is nothing but Henry Mach number. So Henry Mach number we got it as 0.432. So this is one thing. Then this Henry Mach number in the formula we are substituting here. In place of M1, we are substituting this. Okay. So this is this is the value we are here. Okay. This value we have taken and substituted, and we got what is this? Okay. So this is the value we got it, and then the temperature coming around that means stagnation temperature. So nothing but 311.19 Kelvin. Okay. So this value you can verify from your side. Okay. So if you have any changes or any, if you find it anything different, let me know. So with this, okay, we got the answer for the first this question. Okay, that means first question we got the answer. Then let me just go to the next one. Next one is nothing but we have to find out maximum velocity. Okay, so we have to find out maximum velocity. For finding the maximum velocity, we have certain formulas. If you remember correctly, okay, we have got the formula in our okay, while studying about isentropic flows, we got formulas. So that is nothing but you know this is yes. So 2 by gamma minus 1. So this is the formula. So use this formula and then find out, because you know Cmax equal to, so that is A naught is nothing but square root of, that is a stagnation speed of sound. So you know the formula, square root of gamma or T naught into square root of 2 by gamma R1. Okay. So please substitute the values. T naught, you know, just now we got it. The stagnation temperature, just now we got it. Yeah, please substitute. Then it is nothing but square root of 1.4 into gamma is nothing but 1.4. This is nothing but 287.43 into T naught. T naught is nothing but we know 311.19. Okay. So into square root of 2 by 1.4 minus 1. Okay. So you know the formula, then please substitute and then get the value. So Cmax, I think by calculating, you have to find out. Yes. First to calculate what is the value of this one, square root of 1.4 into 287 into 311.19. Then yeah, into square root of yes 2 by 0.4. So yes, it's supposed to be the value of the Cmax, nothing but maximum velocity. So that is becoming around this value is becoming around 790.68. Okay, 790.68. The unit is important, meter per second. Okay. So the Cmax, okay, equal to 790.68 meter per second. So please, we got the second value. Please note down. Then we have to go to the third one. Third one is nothing but mass flow rate. So we have to find out the mass flow rate. We know mass flow rate formula. Okay. So you know the mass flow rate formula, and then we can use that, and we can find out. Okay. So you guys, anyone is, if you know, yes, let me know. What is the mass flow rate formula? So by using the mass flow rate formula, so we got a second value. This is yes. Now let me go for the third one. Yeah, third one is it's nothing but mass flow rate. Okay, so the mass flow rate formula is very simple. Okay, so mass flow rate, that is nothing but m dot. So m dot is this mass flow rate is nothing but rho a b. Okay, so this is because mass flow rate anyway at the entry and the exit should be seen. Okay, since it is a axisymmetric duct and adiabatic flow okay, adiabatic flow condition. So there is no heat losses. So in that case, your mass flow rate will remain constant throughout that. Okay. So anyway, mass flow rate is always constant. Okay. So that is what law of conservation of mass is. So by using this formula, we have to find out. Either you can do one thing. What we can do, either we can take rho one, A1, and V1, because since your area at the inlet is given, okay, area of the cross section at the entry is given, and so because of that we can use this formula. Otherwise, if you know A2, this also can be taken. Here rho 2, A2, V2. So this also can be taken. Am I right? So both of them can be used. Either you can use this or this. So in that case, what we are going to get? Let's see. Yeah. So let me delete this, and then so we have to find out this. Yes. So m dot equal to. Let me use the rho 1 A1 V1 A1 V1. So this is nothing but rho 1. How to find out density? Okay. So that is nothing but that you have to get it from the by using the ideal gas equation. So the ideal gas equation says this is P1 by rho 1 equal to RT1. So in that case, it is rho 1 is nothing but what to say, RT1. That means P1 divided by RT1. So into A1 into V1, because you can take it as this side, P1 by rho 1 equal to RT1. This is nothing but PV, P1 V1, that is the volume. specific volume only becomes the inverse of the specific volume. It's nothing but density. So that's what we just are having P1 by rho 1. So since we know the formula, just substitute the value, and the value also available because the static pressure at the inlet is known and the static temperature at the inlet also known. So substitute the value. T1 is nothing but 3.45. So 3.45 into substitute in Pascal, 10 to the power by. So because we know 1 Pascal, 1 bar equal to 10 to the power by Pascal. So then whole divided by this whole divided by here. Yes, what is the R value? R is nothing but 287.43 into temperature T1. That should be in degree Kelvin. So that is nothing but 300 Kelvin. Sorry, 300. So you can just Kelvin is not required. So okay, so 300 and into you have to substitute A1. The A1 you see here, it is given A1 is nothing but 500 given in centimeter square. Say we wanted that in meter square. So you can take it as into 10 to the power of minus 4. 10 to the power of minus 4 meter square. The centimeter, 1 centimeter square equal to 10 to the power of minus 4 meter square. So I'm just converting into that. Into V1, that velocity at the entry inlet nothing but 150 meter per second. So now we have to calculate. Okay, by doing the calculation, what we are getting. So whole divided by this 287.43 300 to 500. So it's, I think the value is into 150. Yeah. So it is 30.007. Am I right? So that value becomes 30.007. What is the unit? Unit is nothing but kg per second. So please check this value, and this value should be correct. So now we got the third this answer for the